So now let's talk about moment of a couple. And I'm actually not gonna go into too much detail here due to time constraints, but you have some small general notes about couples, and this is actually section 4.6 in your book. So I'd like to just define some of these terms and perhaps explain how to calculate these moments, but we're not gonna go further on that. So I can define a couple as a set of two parallel forces that have the same magnitude but in opposite direction. So in other words, a couple is a set of two parallel forces which have the same magnitude but opposite direction. In other words, if I wanted to draw a couple, I would essentially have one force vector and another force vector, but with the same magnitude. They're parallel, they have the same magnitude, but they act in opposite direction. And couples are very interesting groupings, because let's look at this from a static perspective. If I want to apply the equations of equilibrium, let's call these my x and my y axes. And if I want to find the sum of forces in the y direction, what would that be in this case? If we're looking at these two forces, they both have the same magnitude. What's the sum of forces in the y direction?
0.
Yep, 0. We have our force F minus our force F, which is just 0. So at first glance, it may seem that these forces will have no effect on a system because it just remains a static system. But remember that any force applied at a distance causes a moment, which means that these forces will actually result in a moment. So even though in the y direction or x direction, our forces may be 0, our sum of forces, there will actually be some resulting moment from these two forces. So in other words, this moment is not 0. And what is that moment? The sum of moments that results from a coupled force is simply equal to the magnitude of the force times the distance between the forces. In other words, if my distance between my two forces is d, then the sum of moments, the total moment that these two forces causes, is F sub d. Now there's a couple of interesting things about couples, okay? When we're looking at couples, you may think that we need to figure out where is your point of interest along this line. But we'll see that it doesn't really matter where my point of interest is, because whatever point I choose in between these two forces will actually experience the same moment. So as long as, even if it's not in between, any point that I choose actually will actually experience the same moment from these two forces. And I want to look at some examples, because this is something that we've had a little bit of trouble conceptualizing in previous semesters. So I would like to try out some examples. Let's say that I have a couple. In other words, a set of two forces with the same magnitude, opposite direction. They are parallel. And let's say that this couple is located at a distance of d from each other. Now, let's pretend that I would like to find the moment that these two forces cause about a point. And this point is located right in between these two forces. So first off, what is the distance between my point and my first force? What's this distance?
1/2 d.
Yep, because right in the middle, it'll be just 1/2 d. And of course, the distance between the point and the other force is 1/2 d. So if I want to find the moment that these two forces causes, I need to consider first my first force times a distance of 1/2 d. This is counterclockwise. I'm just going to say it's negative. Oh, this is clockwise. So I'm just going to say it's negative. Plus, I have my second force, which is also F, times 1/2 d. also clockwise, so I'm also going to give it a negative sign. And notice what happens. We can factor out the negative force and d. So I just end up with negative force d 1/2 plus 1/2. And what does this end up giving me? 1/2 times plus 1/2 is just 1. So this just ends up giving me a moment of F times D, which is essentially what the couple moment is. It doesn't matter where you pick your point, you will always end up at a moment being equal to F times D. So if I want to pick my point at 1/3 of my forces, the distance between my point and my first force is 1/3 D. The distance between my point and my second force is 2/3 D. And if I want to find the moment will be equal to negative force times 1/3 D plus negative force times 2/3 D. And this ends up being, once again, just force times distance. So that's the interesting thing about couples. It doesn't matter where you're studying your point, which point you're studying, the moment will actually be the same. It will always be F, that's the magnitude of the force, times the distance between those two forces. Now I'm going to refrain from doing an example because I do want to finish this chapter's materials today. But essentially what you need to know from a couple is that the moment of a couple is F times D. If you'd like, I recommend that you try problems F4-21 and F4-24, and those should give you a good introduction and practice to using coupled moments, okay? So, any questions with couples before I move on to the last topic for today? Okay, if there are no questions, let's finish today's chapter, this chapter 4, by looking at distributed loads. Now, this is actually going to be maybe complicated if you haven't seen it before. So I'm going to try my best to explain it. However, I will warn you that distributed loads actually requires a little bit of understanding of calculus in order to grasp completely. So we'll look at distributed loads, and I'm going to try my best to explain in whatever time is left. When I say the word distributed load, what I essentially mean is a force that is distributed over an area or a length. Now in this class, we can distribute the force over a length. In other words, instead of one force acting at one point, I can have a force acting at every single point of a length. So essentially what I'm looking at is a continuous force that acts at every single point of a length. So how do we quantify this? We're always used to treating forces as vectors, and that's correct. But how do we quantify distributed loadings? Well, we should first understand that because this is a distributed force, the units are going to be force divided by length, because the force actually acts on every single point of the length. So it is distributed over a length. There are different types of distributed loads, and from physics, you may remember some of them. If we remember correctly, if we distribute a force over an area, we have what's essentially a pressure, right? Pressure is force over area. So similarly, we distribute this load over a length, which is just force over length. So you have dealt with distributed forces before, but you may not have called it that before, but you have dealt with them. Just like pressure is a force distributed over an area, our distributed load will be a force distributed over a length. Now, why length? Because in our two-dimensional study, we're going to try to look first at forces in 2 dimensions. However, we can always apply whatever we learned today to the study of pressures as well. Now, how do we calculate these distributed loads? We're going to have to actually resort to calculus. Now, there's a study in calculus called differential analysis where we look at a tiny, 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 tiny length of this bar. In fact, so tiny that we can't even quantify it numerically. In other words, this length is so tiny that I'm going to give it dimensions of dx. Okay, so this is a tiny, tiny, tiny length dx. And this tiny length dx is experiencing a tiny, tiny, tiny column of a distributed load. So this tiny, tiny, tiny column of a distributed load is going to have a magnitude that I'm going to call df. Okay? So what does that mean? This force column has a magnitude of df. And I can break down this magnitude by looking at the geometry of this column. You see, when we deal with distributed loadings, we typically plot our loads as if they were on a XY plane, in this case, two-dimensional case. So I can give a name to this distributed load. Just like a force over an area is called a pressure in physics, we will call a force over a length a load, which we will represent with the variable W. So the height, that is the total load of this column, is my W. And I can quantify my force by saying that my force is my W, that is force over length, times my length dx. Now, if you're not sure where those are coming from, remember, W is force over length. So in order to get force, I need to multiply W times length, because W is force over length, and therefore force is just W times length. So my tiny, tiny, tiny force dF will be equal to W times dx. And why do I care about this? Because differential analysis allows us to find relationships for tiny, tiny, tiny elements and then expand them to apply to a whole body. And how do I expand them? We need to add up all of the tiny, tiny, tiny dx's. However, dx is so small that it doesn't even have dimensions, right? It's the dimension of dx. We can't quantify it. That means that there should be an infinite number of dx's over this bar. So how can we add up an infinite number of elements?
Integration.
That's correct. So we want to find the total sum of all of my tiny df's, which is just my force. We just integrate this expression. Now, here's where things are going to get interesting, because what does W dx represent in this shape? This is simply the area of the force. This is just a little area, dA. So this is the same as saying that force is the integral of all my little areas dA. So if I were to look at all my little areas dA's, and I would add them up, I essentially get my force. So what does this tell me? What this tells me is that the force from a distributed load is equal to the geometric area of that load. In other words, I can find the total force acting on this bar by calculating the area of this force distribution. So before we end today, let's look at two quick examples. Let's look at the example where my force is evenly distributed. In other words, my force has a rectangular distribution with a maximum load of W and a length of L. So what is the total force acting on this bar? We know that the force is equal to the area of the load, and the area for a rectangle is the length times the height. So the total force is WL. We could do the same thing for a triangular distribution with a maximum load L, or W, acting on a bar L. And to finish today's class, what is the force on this triangular distribution?
It's just 1/2 WL.
Yep, 1/2 WL. So that's how you find forces on distributed loads. You're going to try out different examples. Of course, sometimes you'll get equations, so you'll have to do a formal integration. But if your distributed loads are pretty much regular shapes, you should be able to find the force. So we're going to leave it here. We're already out of time. And I would encourage you to just try to work on your homework, email me when you need help, and pay close attention to this. We're going to keep doing this in later chapters, but at least try to get the general idea of force equals the area of distribution. So that being said, I'll just see all of you next week.